Hello all. Today I'm breaking a rule that I set for myself, which is to not engage with paper requests in the comments. Not because I'm a mean person, maybe I am a little bit, I don't know, but mostly because, if this channel ever grows to a lot of subscribers, it's going to be impossible to keep up with something like that. And in addition to that, the channel is not monetized yet, so it's hard to keep going without getting anything out of this yet. So, but anyway, someone requested the paper 2 from 2021, and this is the Edexcel curriculum from the UK. For some reason, they call it level 3 GCE. I don't know what level 3 means. I guess level 1 is the GCSEs, and then maybe level 2 is the AS level. I don't know. Let me know in the comments. So this Advanced Physics 2 from 2021. I'm sorry for my voice. It's last night there was the cup final, the football cup final here in Cyprus, and I went to watch because it was my team playing, and they won. So this is why my voice is broken. I mean, it's it makes it hard to record, but I'm fine. So I'm gonna go over this fast because I want to put it out there today, okay? Because the test is taken on Monday, today is Saturday, so let's go. So I'm not gonna say the usual comments I say every time about tests. Maybe just this one. You should spend about a minute per mark. So if a question awards 10 marks, you should devote about 10 minutes, okay, so that you stay on track and on time and you finish all problems. Okay, let's start with question 1. Ultrasound can be used to investigate the structure of organs of the human body using the pulse echo technique. The level of detail obtained depends on the wavelength and the length of the pulses. Which line of the table shows a change to wavelength and a change to pulse length that would each improve the level of detail? Okay, so basically the option A is the correct one, and I'm going to try to explain it really fast. So the reason why shorter lambda is better is because you get smaller features resolved, okay, in the human body, and therefore better accuracy. Okay, and the reason why a shorter pulse length helps, shorter pulse length, is because pulses don't overlap. Okay, and this gives you better detail. Okay, so option A is the correct one in this case. So both a shorter wavelength helps and a shorter pulse length. Let's move on to question number 2. An object is placed in front of a lens. Which of the table shows a combination that will produce a real image of the object? Okay, first of all, a real image requires a converging lens. Therefore, the first two options are gone, okay, because that's a diverging lens. Diverging lenses have a negative focal point. Okay. And then if the focal length is 5 centimeters, then if we put the object in the 2 centimeters, we don't get a real image either, okay? So that's wrong. So the only correct option is C, okay? Because we have the converging lens, and that's the focal point, which is 5 centimeters. And if we put the object farther away at another 5 centimeters for a total of 10, then we can immediately see that we get a real image. Okay, that's the image. Okay, and this is an example of something I say in most of my videos from Edexcel. I noticed that with the multiple choice questions, it is often the case that you can arrive at the correct answer by eliminating all the wrong answers, like in this example. So Options A and B are obviously wrong because those are diverging lenses. And then option D is also wrong because you have the object within the focal point. Okay, so it doesn't make sense. So only option C works. Okay, let's move on. As I said, I'm gonna go over the problems really fast today. Okay, because the test is taken on Monday. Okay, questions 3 and 4 refer to the following information. A horizontal force F is applied to a horizontal spring fixed at one end. The stiffness of the spring is K and the elastic strain energy stored is E. A second identical spring is added and the same force is applied to the combination of springs as shown. What is the stiffness of the combination of springs? So for springs in series, 1 over the total spring constant is 1 over K plus 1 over K. Okay, so K total is K over 2, which is option A. Okay, and then for question 4, what is the elastic strain energy stored for the combination of springs? So you see that the same force F is pretty much acting on both springs, okay? And also the springs are gonna be extended by the same delta x, okay? So for one spring, the energy stored is 1/2 F times delta x. So since the same F is applied to both, so same delta x extension for both, then the total energy is simply 2 times E, okay? So option C. Again, forgive me for my voice. Yeah, I was at the football match yesterday and I was shouting at some point. I mean, chanting, you know, this kind of thing. So my voice is broken. So I'm sorry, guys. So let's move on. Option 5. A mass of 24 kilograms is suspended from a steel wire of length 1.5 meters. The wire has cross-sectional area of 3.1 times 10 to the negative 6 square meters. The Young modulus of steel is 1.8 times 10 to the 11 pascals. Which of the following gives the extension of the wire? So let's start. Stress is strain times the Young modulus, but stress is force per cross-sectional area. Strain is delta x over the length times the Young's modulus. So delta x is force times length over cross-sectional area times the Young's modulus. Now the force is, I'm gonna do this and say that the force is mass times g, right? So let's form a fraction. So the force is 24 times 9.81, which is mass times g, times the length, which is 1.5, over the cross-sectional area, 3.1 times 10 to the negative 6, times the Young's modulus, which is 1.8 times 10 to the 11, and therefore that's option B. Okay, and again, I didn't look into this problem in detail, but I mean, from a quick glance, you can see that A doesn't work, C doesn't work, and D doesn't work. And I'm gonna let you find out why they don't work. Let me know in the comments actually, okay? But think about the units, okay? That's the hint. And tell me why A, C, and D cannot work in this case. In which case, again, you see that just by physics intuition, you can arrive at the correct answer. And also, let me know in the comments again, what are the units for delta x, okay? Now, let's go to question number 6. Okay, now let's go to question number 6. The diagram shows a source of sound waves and an observer. Which of the table shows a situation which would result in a decrease in the frequency of sound observed. Okay, before we solve this, let's write down that v, the velocity of a wave, is lambda times its frequency. So the frequency is velocity over lambda. Okay, so if lambda increases, f decreases. Right? Okay, so let's think. Option A, the source moves to the right at 20 meters per second, and the observer moves to the left. So this will result in the wavelength getting squeezed, right? And so it's gonna get shorter. So this is not what we want. Then option B, the source moves to the right at 20 meters per second, and the observer also moves to the right at 20 meters per second. So the two motions will cancel each other, so that's wrong as well. Okay, let's go to option C. We have the source moving to the right at 20 meters per second. Again, in this scenario, the wavelength is going to get squeezed. Okay, so we will have a shorter wavelength, so C is wrong with the observer stationary. Okay, and then option D, we have the source stationary and the observer moving to the right at 20 meters per second, which is gonna make the wavelength appear, get larger, which is exactly what we need. So D is the correct answer. And you have to think about the Doppler effect here. So if this guy moves away, then the wave fronts are gonna get farther away. If this guy moves to the right, sorry, to the left, then the wavelengths are gonna get closer together, okay, which is what would not what we want. So option D is the correct one. Let's move on to question number 7. The photoelectric effect provides evidence for the particle nature of electromagnetic radiation. Which of the following observations of the photoelectric effect could also be explained using the wave nature of electromagnetic radiation? Okay. Option A, the emission of photoelectrons is instantaneous. That's only explained by the particle nature, so no. B, the maximum kinetic energy of photoelectrons depends on frequency, also explained by the particle nature, so no. Then C, the rate of emission of photoelectrons depends on intensity. Okay, that's the answer. Okay, and let's read D as well. There is a minimum frequency for emission of photoelectrons to occur. That's also only explained by the particle nature. So C. Okay. Let's move on to question number 8. The acceleration of free fall at the surface of the Earth is 9.81 meters per second squared. The mass of the Earth is m, and the diameter of the Earth is d. Which of the following gives the acceleration of free fall in meters per second squared at the surface of a planet with diameter d over 2 and mass m over 9? If I'm not mistaken, that's Mars, but let me know in the comments. Okay, so G on Earth is the gravitational constant times the mass of the Earth over d squared over 4, okay? And that's because r is d over 2, so r squared is d squared over 4, okay? Now let's do G prime on this planet. We will have G times the mass is mass over 9 over d over 2, which will have to make d over 4, so d squared over 16. So we have 4 over 9 times 4gm over d squared, and this is g, so the answer is B. Okay, moving on. Question 9, a mass is suspended from a spring and allowed to come to equilibrium. The mass is displaced vertically and moves with simple harmonic motion. The graph shows how the resultant force on the mass varies with time. Which of the following graphs shows how the velocity v of the mass varies with time t over the same time interval? Okay, so the way I went over this is that force, there are many ways to solve this, but I went with this one. So force is minus k over x, which means that x is minus f over m, which means that the displacement is going to look like this, okay? So that's displacement. And therefore, if I take the gradient where the oscillation starts, this gradient is negative, okay? Which means that the initial velocity is negative, and the velocity has to be a cosine function, okay? And cosine functions start at, if you plot cosine x with x, okay, they start up there, okay, or down here. So, since the initial velocity is negative, the only option that works is B, okay? And again, here we can immediately, since they give us the force with time looking like a sine function, we can immediately infer that options A and C are wrong, okay? So all we have to do is to figure out whether it's B or D. But again, because the initial velocity is negative, then we know immediately that option B is the correct answer. Okay, and let's move on to question number 10, which is the last multiple choice question. So the diagram represents an arrangement used to generate standing waves on a string. So you have a vibration generator, a string, a pulley, and masses on mass hanger. A standing wave pattern with two nodes is obtained as shown. Which of the following single changes could produce a standing wave pattern with three nodes? So let me write a few things. Maybe I'm going to use a clean page. So we need to feed three nodes into the same length what am I doing? Three nodes into the same length, which means fitting one full lambda in the strings length. In other words, we have this situation, right? Okay, and L, the length of this string is going to be half a wavelength, and we need to convert it into, let's use red, so we have three nodes now, so we have to convert it into this picture, okay? So in this case, L is going to be lambda, okay? Let's call it lambda prime because it's a different wavelength, okay? Okay, so the wavelength, thus lambda, must halve, okay? And because lambda times f is equal to v, comma, v must decrease. Which makes sense if you think about it. I mean, with a lower velocity, it's easier to feed one wavelength, right? Okay, but the velocity is the square root of t over nu, the mass per unit length. So t must decrease. And t is provided by the mass hanging there, like the weight of the masses. So mass decrease. So mass must decrease. Okay, I'm sure there is an easier way to solve this, okay? But I went the extra mile to try to explain what's going on. So we need the mass to decrease. So let's read the options. Decreasing the distance between the vibration generator and pulley, that's going to make our lives harder, actually. So no. B, decreasing the frequency of the vibration generator, that's not going to cut it. C, decreasing the mass on the mass hanger, which is what we are looking for. And then D, decreasing the mass per unit length of the string. That's going to increase the velocity, actually. So no. Okay, this was the multiple choice section. Let's move on to the questions now. Okay, question 11. A simple pendulum consisting of a thread and a bob is set up next to a horizontal rod. The bob is displaced to the left and decreased and released. Excuse me, I don't know what's wrong with me today. Okay, when the bob reaches the equilibrium position, the thread strikes the horizontal rod for half of the cycle. Okay, so that's a key there. For half of the cycle, only the lower part of the pendulum moves. The diagram shows the swing of the pendulum. Okay, so you see the situation. The bob moves to the left, finds the rod, and then it oscillates that way. Okay. Now the question, where is the question? There is no question yet. So the diagram below shows the dimensions of the pendulum. Okay, that's good. Determine the frequency of the oscillations of the pendulum. So we basically have to find the period of oscillation for this string and for this, okay? And then add and divide by 2 pretty much and find the average, okay? So the first period, T1, for the longer string is 2 pi, the square root of L1 over G. So 2 pi times the square root of 0.67 over 9.81, which is 1.64 seconds. And then the second period is 2 pi, and then the square root of L2 over G. So 2 pi, and then the square root of 0.67 minus 0.24 over 9.81, which yields 1.32 seconds. So for half a cycle, we have the large string oscillating, and for the other half, we have the shorter string oscillating. So we just have to take the average between these two periods. So let's call it T total. Actually, no, T average is the correct expression. It's going to be T1 plus T2 over 2, or 1.48 seconds. Don't forget that they ask for the frequency, okay? So F average is 1 over T average, or 0.68 hertz. Okay, let's move on to question 12. So latte is a type of coffee that vain people, no, sorry. Latte is a type of coffee made with hot frothy milk. Okay, you don't have to be what did I say? Vain. You don't have to say you don't have to be vain to drink latte. But I don't know. Here in Cyprus, coffee became something of a religion, and I really don't like it. I like coffee. I don't like the culture around it, because people tell you, I'm having my cappuccino, Freddo, whatever, with cinnamon. It's like, who cares, I mean, it's just coffee, but anyway, let me know what's going on in other areas of the world, but it's crazy here. Okay, so latte is a type of coffee made with hot frothy milk. The milk is heated by pumping steam into it. Calculate the maximum mass of milk that could be warmed to a temperature of 65 degrees Celsius by absorbing 15 grams of steam at 100 degrees Celsius. And they give you the initial temperature of milk, specific heat capacity of milk and water, and the specific latent heat of vaporization of water. Okay, so we pretty much have to set an equation here. So the specific heat capacity of milk, let's call it Cm, times the mass of milk times the temperature change for milk. Okay. I mean, the energy needed to do this is going to be provided by the steam first becoming a liquid, which means that we need the mass of steam times the latent heat of steam. Okay, so we first have to make steam into water. Okay, and then once it becomes water, that same mass of steam has to cool down to 65 degrees Celsius from 100 degrees Celsius. So we will need the specific heat capacity of water times the mass of steam, and I'm gonna put there that steam is now water. Okay, don't forget that. Times the temperature change for the steam. Okay, so this energy from the cooling down of the steam is gonna go into the milk warming up. Okay, so let's plug in numbers. We have 3,900 times the mass of milk, which is actually unknown, right? This is what we are looking to find, times the temperature change, which is 65 minus 4, right? Don't forget, by the way, that I'm going to write it up here. So delta theta for Cm delta theta can be expressed in Celsius. So what I'm trying to say is that the same temperature change in Kelvin is exactly the same temperature change in Celsius, because if you convert to Kelvin, all you will do in this case is going to be, okay, 65 is going to be 273 plus 65, and then you have to subtract minus the temperature change for, sorry, the Kelvin for 4 degrees Celsius, which is 273 plus 4, right? So the 273 cancels anyway. So the same temperature change in Celsius is the same temperature change in Kelvin. Okay, so the mass of steam is 0.015 kilograms times 2.3 times 10 to the 6 plus 4,200 times 0.015 times the temperature change, which is 100 minus 65, right? So we have 237,900 times m milk is equal to 36,705. Okay, so m of milk is 154 kilograms, which is also equal to 154 grams. Okay, so this was question 12, and I'm going to take a break and drink some water because my voice is, I don't know, it's really broken. Okay, so I'll be back in a few. Okay, let's move on to question 13 now. Okay, there is an asterisk, which means a long writing problem, 6 marks. So in general, with these types of questions where you don't do calculations, you just have to provide an answer for something. If it awards 6 marks, it's good to provide about 5 to 7 sentences to be sure that you get full points. If it awards 3 marks, you have to provide 3 sentences. When I say sentences, I mean independent statements about whatever the question is, okay? So let's go read 13. The energy radiated by stars is released by nuclear fusion. Explain the conditions required to bring about and maintain nuclear fusions in stars. So let's start by saying that nuclei are positively charged. Okay. Hence, there is a large electrostatic repulsion between them. Okay, so that's the first sentence. So very high temperature is required so that nuclei have high kinetic energy. Okay, so that's the second requirement. Then at sufficient kinetic energy, Okay, nuclei can overcome the electrostatic repulsion. Okay, nuclei must approach close enough for the strong nuclear force to act and bind them. And recall here that the nuclear force is very attractive, more attractive than the electromagnetic force, about 100 times more attractive, but the nuclei have to be really close together for that force to act. Otherwise, it's not even felt. Okay. And the other thing is that very high density is also required. So very high density is also required. Okay. And lastly, this density, high density ensures the collision rate is high enough to sustain fusion continuously. All right, so this was question 13. Let's move on to the next one. Okay, question 14. A student investigated the terminal velocity of steel spheres falling through oil. The student, obtained the following results. We have the radius of the sphere, the volume of the sphere. I don't know why they give us that. I mean, you can calculate it from the radius, but anyway, the mass of steel sphere and the maximum speed of sphere. The student had the following table: type of oil and viscosity and density. So you see that the density is the same for all, but the viscosity is different. So identify which type of oil the student used. Okay, so you have to set up the equation for terminal velocity. Okay, so V terminal means that the acceleration is zero, which means that the sum of all forces is zero. So what are the forces on a ball falling through oil? It's of course its weight, the upthrust, and the drag force. Okay, so you see that sigma F, if we take down as the positive direction since the ball is falling down, is weight minus drag minus upthrust, and this is zero. Okay, so the equation is d plus u, drag plus upthrust, is equal to the weight. Now the drag force is the Stokes force, which is 6 pi times the radius of the sphere times the viscosity of the liquid times the terminal velocity in this case. Okay, it's v in general, but here it's the terminal velocity. Okay, plus the density of the liquid times g, that's the mass of the liquid, times the displaced volume of liquid, which is equal to the volume of the sphere. And this whole thing is going to be equal to the mass of the sphere times g. Okay, now let's plug in numbers. So 6 pi times the radius, which is 1.5 times 10 to the negative 3 times 0, 849, which is the terminal velocity, times eta, the viscosity, since we don't know it and we are searching for it. Okay, plus 918, which is the density, times yes, the density of the liquid times 9.81, the acceleration of gravity times 1.41 times 10 to the negative 8 cubic meters, which is the volume which we just use. Okay, maybe we save a few seconds. Okay, and this is equal to 1.1 times 10 to the negative 4, which is the mass in kilograms of the sphere, times 9.81. Too many numbers, so it's easy to mess up this one. Okay, so 0.024 eta plus 1.27 times 10 to the negative 4 is equal to 108 times 10 to the negative 3, excuse me. Okay. Okay, so eta times 0.024 is equal to 9.52 times 10 to the negative 4. So eta is simply 0.0397 pascals times seconds, which is closer to sunflower oil. Okay, that's the answer. Let's move on to part B. The values in the table are for oil at 26 degrees Celsius. Explain the effect of carrying out the investigation with oil at a lower temperature. I'm going to do this really fast. So as the temperature decreases, the viscosity increases, okay, because oil is thicker. Okay, so since the viscosity increases, then the drag increases, so V terminal decreases. Okay, so that's the answer to part B. All right, let's move on. '15. One of the largest stars in our galaxy is VY Canis Majoris, something like that. This star's radius is 1,420 times the radius of the Sun. The luminosity of the star is 270,000 times the luminosity of the Sun. Okay. A student states that the surface temperature of VY Canis Majoris must be much greater than the surface temperature of the Sun. A, determine whether the student's statement is correct. Okay, so let us start by, okay, we pretty much have to calculate the surface temperature of Canis Majoris. So let's use the Stefan Boltzmann's law, which is for the luminosity of Canis Majoris. So L is sigma A T to the fourth, but the luminosity of Canis Majoris is 270,000 times the luminosity of the Sun, which is sigma times the times the surface area of the Sun times the Sun's temperature to the fourth, and this must be equal to sigma times times the surface area of Canis Majoris times the temperature of Canis Majoris to the fourth. Okay, so we can cancel sigma in both sides. That's nice. Okay, and let's solve for Tc to the fourth. So Tc to the fourth is 270,000 times the surface area of the Sun over the surface area of Canis Majoris times the temperature of the Sun to the fourth. Okay, so Tc to the fourth is 270,000 times the surface area of the Sun, which is 4 pi times r of the Sun squared. And then for Canis Majoris, we have 4 pi r c squared, so 4 pi cancels, times the surface temperature of the Sun to the fourth. But then we are given this relationship for the radius of Canis Majoris. Okay, so I'm going to use a clean page to carry on. So the temperature of Canis Majoris to the fourth is 270,000 times the radius of the Sun, over 1420 squared times the radius of the sun squared, which is the radius of Canis Majoris, times Ts to the fourth. Okay, so Tc to the fourth is 0.134 times 5780 to the fourth. Okay, so Tc is finally 3496.4 degrees Kelvin, which is less than the temperature of the sun. Okay, this was the question, I think. And the student states that the surface temperature of Canis Majoris must be greater than the surface temperature of the sun. So we can say that student is wrong. Okay. This took longer than I expected, but okay, let's move on. B. Calculate the wavelength with maximum intensity in the blackbody radiation spectrum of Vy Canis Majoris. So we're going to use Wien's law. Lambda times the temperature is equal to this constant. Okay. So lambda is 2.898 times 10 to the negative 3 meters times Kelvin over 3,496.4 kelvins, okay, which is 8.29 times 10 to the negative 7 meters, which is 828.8 nanometers. So that's infrared radiation for the record, okay. So let's move on to C. Add the position of Vy Canis Majoris to the Hertzsprung-Russell diagram to determine which type of star it is. So it's gonna be somewhere here, pretty much, okay? The type of star is a red giant. Okay, because okay, that's about 3,800, and this is about 270,000 the luminosity of the sun. Okay, yeah. So this is the answer. Okay, question 16. The Planck constant can be determined in a school laboratory using light-emitting diodes. An LED emits light when the potential difference across it is large enough to transfer sufficient energy to an electron to result in the emission of a photon. The electron must have energy greater than or equal to the photon energy. The minimum potential difference required to produce light from LEDs emitting different frequencies was measured by increasing the potential difference from 0 until light was first seen. Okay, so this is similar to the photoelectric effect, but the difference is that you now provide energy to the electron and the electron emits the photon. Okay, so in the photoelectric effect, you have the photon absorbed by the electron. Okay, so it's a little bit tricky, not that tricky though. So let's see. Question A, determine the value of the Planck constant given by this graph. Okay, let's start with the photoelectric equation. So H times F is equal to the, is equal to the work function plus the kinetic energy max of the electrons, but this kinetic energy max is going to be provided by the potential difference. Okay, so E times V. So let's write this down. So H times F is going to be equal to the work function plus E times V, okay, because the electrons acquire this kinetic energy by the potential, okay, and the potential, remember that the work done by the electric potential is Q times V, so that's why we put E times V. Now let's solve for this potential difference. So V is H over E times the frequency minus the work function over E, okay? So this has the form Y equals to mx plus c. So I'm going to use a clean page. So the gradient is going to be H over E, but the gradient is delta V over delta F. Okay, so if we combine, we see that H is E times delta V over delta F. Okay, so 1.6 times 10 to the negative 19 times delta V. Let's go to the graph. I chose this point here, and what else did I do? And this point, actually, okay? And pay attention to where these graphs start, because that's not the zero of either the voltage or the frequency, okay? So we have 2.4 minus 1 volts in the numerator, and this 2.4 volts corresponds to 6.95 times 10 to the 14 hertz, and then 1 corresponds to 4 times 10 to the 14. And by the way, I skipped the units. So the units are for the charge, you have the coulomb. For the voltage, we can substitute the voltage for joules per coulomb. Okay, so that's the volt. Okay. What else do we have? And then for the hertz, you have seconds in the numerator. Okay, so coulombs cancel. So we see that H is 7.59 times 10 to the negative 34 joules times seconds. A little bit too high, but yeah, I mean, this is what we can find. All right, let's go back and read question B. There are two problems with using LEDs to determine the Planck constant. When the potential difference is increased and the LED first emits light, it is difficult to see. The LEDs do not emit a single frequency, but also light of frequencies slightly above and below the recorded frequency. Discuss the extent to which these problems are consistent with obtaining a result from this graph for the Planck constant, which is higher than the accepted value. So, the experimenter keeps increasing V past the true threshold. Okay, before seeing the light. Okay, so this might create the problem that the recorded V is too high. Okay, which means that data points move upwards. Okay, and increase the gradient, hence H increases. Okay, then let's okay, we have this space here, so let's write here for part B. Then the other issue is that light of frequencies slightly above the stated frequency okay is also present. Okay, this light may be seen first. Okay, so V may correspond to a lower F than stated. Okay, this reduces the gradient and H. Okay, I need another clean page. So problem one, I mean estimating the gradient. So problem one pushes up and problem two down. But in our case, the pushing up one, okay? I mean, from what we saw, the pushing up dominated. Okay, and that's the answer to question 16. We are ready to move on to the next one. Okay, question 17. Astronomers observing stars at the center of our galaxy have suggested that many of them are orbiting a supermassive black hole. And there's also a really nice song by Muse. I think it's an English band, right? Let me know in the comments. So, the mass of this black hole is 9.2 times 10 to the 36 kilograms. Calculate the orbital period for a star in a circular orbit, orbit at a distance of 1.9 times 10 to the 14 meters from a black hole of this mass. So, we'll start by stating that the force of gravity provides the centripetal force for this case, so m omega squared times r. The force of gravity, and m is the mass of the star. So g times capital M is the mass of the black hole times the mass of the star over r squared is m, and then let's convert omega into 4 pi squared over t squared times r. So m cancels. So we have that t squared is 4 pi squared times r to the cubed over g times m, and I usually just plug in numbers now and take the square root at the end. Okay, so let's plug in numbers, and I'm gonna use a clean page. So we have 4 pi squared times 1.9 times 10 to the 14 cubed, okay, over 6.67 times 10 to the negative 11 times 9.2 times 10 to the 36. Okay, so these are all the numbers. The units are second squared. Okay, do I need to work it out? Maybe we can work it out. So we have meters cubed, and then in the numerator we have in the denominator we have newtons, meters squared, kilograms squared, and then we have kilograms in the denominator, so kilograms cancel, these meters cancel. So we have kilograms times meters over newtons. So we end up, let's write the final result. So 4.41 times 10 to the 17. And then we have kilograms times meters, and then newtons are kilograms times meters over second squared. Okay, so if we take the square root of this, we find t is 6.64 times 10 to the 8 seconds, which is the answer. Okay, out of curiosity, I converted this to years, which is 21.1 years. Okay, part B, the star S0-2. This sounds like the name of something that Elon Musk would come with, maybe a child or whatever, a new device or something. So the star S0-2 is in a highly elliptical orbit around the position of the black hole. At its point of closest approach, S0-2 is at a distance of 1.8 times 10 to the 13 meters from the center of the black hole. At the most distant point of its orbit, S0-2 is 2.7 times 10 to the 14 meters from the black hole. Show that the change in gravitational potential energy between the closest and most distant points in this orbit is about 3 times 10 to the 13 joules per kilogram. So let's do this like this. So the potential at the closest approach is g times the mass of the black hole over r close, and then v far at the farthest distance is g times m over r far. So delta v is v close minus v far, so that's gm, and then 1 over r close minus 1 over r far. Okay, so this is, let's move on. So this is 6.67 times 10 to the negative 11 times 9.2 times 10 to the 36 times 1 over 1.8 times 10 to the 13 minus 1 over 2.7 times 10 to the 14. Okay, and the units are in newtons times meter squared over kilograms squared from G, and then we have kilograms for the mass, and then we have meters in the denominator. So what are these units? Now I'm confused. Yeah, this is joules per kilograms, because newtons times meter is joules. Sorry, I got confused for a moment. And then, yeah, okay, that works. And anyway, if we perform the calculation, we find 3.18 times 10 to the 13 joules per kilogram, okay, which is about 3 times 10 to the 13 joules per kilogram as stated. Okay, the second part of part B, at its point of closest approach, the star is traveling at a speed of 8.1 times 10 to the 6 meters per second. Calculate the speed of S0-2 at the farthest point in its orbit using the change in gravitational potential, and they give us the mass of the star. Okay, so at the closest approach, it's going to have the fastest speed, okay? So at the farthest point away, it's going to have the lowest speed. In any case, the change in kinetic energy is going to be equal to the change in gravitational potential energy. So 1/2 times the mass of the star times v1 squared minus 1/2 m times v2 squared is going to be equal to the mass times the change in gravitational potential. So the mass actually cancels, and we don't need it. And v1 is going to be the close distance, and v2 is going to be the farthest away. So let's call it close, and let's call this far. Okay, so let's reach final expression. So I'm going to solve for, first of all, let's do v1 squared minus v2 squared is equal to 2 times the change in gravitational potential. So v2 squared is simply v1 squared minus 2 delta v. So let's plug in the numbers for the squared expressions. So 8.1 times 10 to the 6 squared minus 2 times 3.18 times 10 to the 13 yields 2.01 times 10 to the 12 meters squared, second squared. And if we take the square root, we find that V2 is 1.42 times 10 to the 6 meters per second. Okay, and that's the answer. Okay, is there anything else I want to say here? Where was delta V? Over here. No. Okay, part C. Trigonometric parallax and Hubble's law are two methods used to determine astronomical distances. Explain whether either of these methods is suitable to determine the distance to S0-2. Okay, Hubble's law applies to other galaxies, like really huge distances, so it doesn't work here. So Hubble's law is used for distant galaxies. Okay, so not useful. But parallax works for stars in our galaxy. Okay, so yeah, parallax works. Okay, Is there anything else I want to say? So since S0-2 is local, okay, the parallax shift can be measured. Okay, so this was question 17. Let's move on to the next question. Okay, I've never seen this before. I don't know what it is. It's the game, toy. I don't know. Let me know in the comments. So the photographs, yeah, show a wooden pop gun before and after the cork is popped. The diagram shows a cross section through the pop gun. Okay, so you push that thing in and the cork explodes. I mean, it goes out, something like that. Initially, the piston is at the right-hand end of the cylinder as shown. When the cork is pushed into the other end of the cylinder, then the cork is pushed into the other end of the cylinder. When the handle is pushed in, the pressure of the air in the cylinder increases. This exerts an additional force on the cork. Once the additional force is sufficient to overcome the frictional force between the cork and the cylinder, the cork is pushed out. Show that the pressure of the air in the cylinder must be around 2 times 10 to the 5 pascals in order to push the cork out, and they give you the maximum frictional force, the cross-sectional area, and the atmospheric pressure. So basically, the difference between the pressure in the cylinder minus the atmospheric pressure, right, times the cross-sectional area should be equal to the cross-sectional force, okay? Where P cylinder is when we push it, and P atmosphere is when the cork is released, okay? I hope this makes sense. But we need to find P cylinder, okay? So let's work this out. So P cylinder minus P atmospheric when the cork is pushed out is F over A, where F is the frictional force. So P cylinder is P atmospheric plus F over A. Okay, so let's plug in numbers. I'm going to use a clean page. So this is part A. Okay, so 8.8 over 9.2 times 10 to the negative 5 plus 1 times 10 to the 5 yields 1.96 times 10 to the 5 pascals, which is indeed about 2 times 10 to the 5 pascals. Okay, so this was part A. Okay, part B, calculate the temperature of the gas in the cylinder at the instant the cork is expelled. And they give you the volume of air in the cylinder with the handle pulled out. Volume of air at the moment the cork is pushed out, the atmospheric pressure, and the initial temperature of air. So when the cork is just there sitting, we have P atmospheric times V. Let's call it, what shall we call it? Let me think. V, I don't know, atmospheric, maybe. Okay, so this should be NKT atmospheric, which is, okay, the 19 degrees Celsius. When we push it in, so P pushed times V pushed is NKT pushed. Okay, I hope this makes sense. If we divide this, I'm gonna need a new page, but okay, N and K cancel, so that's nice. So let's move on to a clean page. So we have P atmospheric times V times T atmospheric over P pushed times V pushed is equal to T when T atmospheric is the 19 degrees Celsius over T pushed. And T pushed is what we need to find. So T pushed is equal to P pushed times V pushed over P atmospheric times V atmospheric times T atmospheric. I'm sorry. I think I'm using poor wording here, but I hope it makes sense. So the pressure when we push the thing in is 1.96 times 10 to the negative 5. We just calculated that. And then the volume is 6.7 times 10 to the negative 6, which is what they give us, right? Okay, the temperature of 19 degrees has to be converted to Kelvin, and then in the denominator we have the atmospheric pressure 1 times 10 to the 5, and then the volume, which is 1.1 times 10 to the negative 5, which is the initial volume pretty much before we push the thing in. Okay, and this yields 1.19 times 292, which is 348.6 Kelvin, which is 75.6 degrees Celsius. Okay, so the temperature increases significantly. Okay, so this was part B. Okay, part C, the formula sheet for this paper includes the equation PV equals 1/3 N times M times the average squared velocity. Okay, derive the equation 1/2 M times the average squared velocity is equal to 3/2 kT. So let's substitute the ideal gas law here. So that's NKT, right? So NKT is 1/3 Nm times the average squared velocity. Okay, so we have to multiply by 3 and then divide by 2. KT is 1/2 mc squared, and we proved it. Okay, D. Calculate the root mean squared speed of the molecules of air in the cylinder before the handle is pushed in. And they give you the average mass of molecule of air and the temperature, which is all we need. So C squared is 3 kT over m. So 3 times 1.38 times 10 to the negative 23 times 292 over 4.8 times 10 to the negative 26. And the units are joules per Kelvin times kelvins over kilograms. Okay, and this I'm going to use a clean page. And this is equal to 251,850 meters squared over second squared. And I'm going to show you now that joules over kilograms works out to be meter squared over second squared, because 1 joule is 1 kilogram times meter squared over second squared, and then over kilograms. Okay, so yeah, that works out. But don't forget that we have to take the square root, right, of that. So the root mean squared velocity of these molecules are 501.85 meters per second, which is about 502 meters per second, which is our answer. This was problem 18. Let's move on to problem 19. Okay, 19. The lens in the eye of an octopus focuses light onto the retina at the back of the eye. The octopus focuses an object at different distances from the eye by changing the shape of the eye to move the lens closer to or further from the retina. A. The power of an octopus lens is 118 diopter. I figured out what the correct pronunciation is for a diopter. Okay. Show that the focal length of the lens is about 8.5 millimeters. So F is 1 over the power of the lens. So 1 over 118 diopter, which yields 8.47 times 10 to the negative 3 meters, which is about indeed 8.5 millimeters. 2. Calculate the shortest distance from the eye at which an object may be focused clearly on the retina. And the maximum distance from lens to retina is 2 centimeters. So basically, we have to use 1 over u plus 1 over v is 1 over f. So 1 over u is going to be 1 over f minus 1 over v. And v is going to be set to 2 centimeters because that's the maximum distance from lens to retina. And that's the distance where the image has to see it, okay? So 1 over 8.47 times 10 to the negative 3, okay, minus 1 over 2 times 10 to the negative 2, and this yields 68, okay. So if we invert it, we find u is 14.7 millimeters. Okay, let's move on. Okay, part 3 is a conceptual question. I mean, we have to write down the answer. It's not a calculation problem. So the lens in the eye of an octopus is in contact with seawater. The refractive index of fresh water is less than the refractive index of seawater. Deduce what will happen to the shortest distance from the eye at which an object may be focused clearly if the octopus was in fresh water. So let's write down that fresh water has a lower refractive index than seawater. Okay, so there is greater refraction of light. Okay, the lens is more powerful in fresh water. Okay, so focal length is shorter, and I'm gonna move to the back. So using 1 over u plus 1 over v is 1 over f with smaller f and fixed v. Okay, u decreases. Okay, so the shortest distance also decreases. Okay, and that's the answer. Moving on to part 4, calculate the speed of light in seawater, and they give us the refractive index of seawater. So that's simply v c over the refractive index. So 3 over 1.37 times 10 to the 8, which yields 2.19 times 10 to the 8 meters per second. And finally, an octopus can detect the orientation of polarized light. State what is meant by polarized light. That's actually impressive. I didn't know octopuses can do that. I think they have like 6 hearts or something like that and 2 brains. I don't know. It's an alien creature. So let me know in the comments if you know more about that. So, So oscillations are confined. This is the definition of polarized light. So oscillations are confined to a single plane. Okay, the plane includes the direction of propagation. Okay, question 20. The photograph shows a vase made of uranium glass. Uranium glass is radioactive. Uranium glass usually contains a maximum of 2% uranium. Uranium glass made in the early part of the 20th century can contain up to 25% uranium. A student carried out an investigation to determine the percentage of uranium in the glass. The student measured the count rate by placing a Geiger-Müller tube against the vase at a single position. This value was used to calculate the decay rate for the whole vase. Part 1, show that the decay constant of uranium is about 5 times 10 to the negative 18 seconds to the minus 1, and they give you the half-life. So lambda is ln of 2 over the half-life. So ln of 2 over 1.41 times 10 to the 17, and we're gonna have seconds to the minus 1. So we get 4.92 times 10 to the negative 18 seconds to the minus 1, which is about 5 times 10 to the negative 18 seconds to the minus 1 as asked. Moving on. Part 2, calculate the percentage of uranium by mass in the glass. This was a highly involved problem, so I think it was hard, but let's go over it step by step. So they give us the area of the GM tube window, the surface area of the whole vase, the the background count rate, the count rate when the GM tube is next to the vase, the mass of the vase, and the mass of uranium atoms. So why do we need all these? You will see. So let's go back to the vase. So first of all, the vase emits radioactive radiation in all directions. But we come here with our Geiger-Müller tube, and maybe we place the window there, okay, and that's our tube, okay? So only a percentage of this radiation is measured by the Geiger-Müller tube, because only a percentage of the whole radiation goes through that window, right? I mean, it makes sense. So let's do some preliminary calculations that we need. So first of all, the background count is 525 counts in 10 minutes. So let's convert this to counts per second. So 525 over 10 times 60 for 60 seconds. This yields 0.88 counts per second. Now let's do the counts from GM window. This is 3,623 counts in 5 minutes, so 5 times 60. This yields 20.08 counts per second. So the corrected count is going to be 1208 minus 0.88 from the background. So 11.2 counts per second is the true rate. Okay, now I'm going to move to the back of the paper to continue. Now, next comes the percentage. Okay, so the area of the vase over the area of the GM window is going to be equal to the total activity, A total, okay, over the A measured. And the A measured is 11.2 counts per second, which we just calculated, okay? So A total is going to be 0.0177, which is the area, okay, square meters, the area of the vase, over 6.36 times 10 to the negative 5 meters squared is the area of the Geiger-Müller window, times 11.2 counts per second, okay? And this gives us the total activity as 3,116.99 counts per second. You can round to, I mean, if you want, you can round to 3,117 counts per second. It's going to be fine. Okay? Now, the total activity is simply equal to lambda times n, right? So we can calculate the number of nucleons that give rise to that activity, right? So n is simply A total over lambda, okay? So we have 3,117 counts per second. I rounded the value, I'm sorry, okay? Over 4.92 times 10 to the negative 8 seconds to the minus 1. Okay, this gives us a pure number. So n is simply 6.34 times 10 to the 20 nuclei. Okay, what is the mass of those nuclei? So the mass is going to be equal to n times the mass of one uranium atom, right? So 6.34 times 10 to the 20 times 238 times 1.66 times 10 to the negative 27, which is the mass of one atomic mass unit. And we finally get 2.5 times 10 to the negative 4 kilograms for the mass of uranium in this glass, okay? And all you have to do now is to divide, so mass of uranium over mass of the vase times 100 yields 0.17% for the percentage of uranium in this glass. So they tell us in the beginning that uranium glass usually contains a maximum of 2% uranium. So yeah, this is a modern vase, I'm trying to say, because they say that uranium glass made in the early part of the 20th century can contain up to 25% uranium. Okay, so that's not the case for us. So yeah, that was part. Which part was that? 2. Okay, part 3. The uranium decays by emitting alpha particles. Criticize the method used to determine the percentage of uranium in the vase. So alpha particles could be absorbed by the glass itself. That's one issue with this method. Before reaching the Geiger-Müller tube. Okay, that's one issue. Then alpha particles are emitted in all directions. Okay, not just toward the detector. Okay, so only a fraction is counted. Okay, I'm gonna need another page. Then some counts, okay, may come from other decay products of uranium and not uranium-238 itself. So this gives you kind of like false counts, okay? And the final issue is that some of the alphas may be absorbed by the GM window. Okay, so this will kind of mess up with the method and the experiment. Okay, moving on. Part B, a uranium nucleus decays to thorium by emission of an alpha particle. It can be assumed that all the energy of the decay is transferred to kinetic energy of the alpha particle. Calculate the speed of the emitted alpha particle. Okay, first of all, let's find how much energy you have available for this alpha particle. So delta M, the change in mass, is going to be equal to the mass of uranium minus the mass of the thorium minus the mass of the alpha. So this yields 4.6 times 10 to the negative 3 atomic mass units, which is equal to 7.636 times 10 to the negative 30 kilograms. And then delta E is delta M C squared, Einstein's relationship. So 7.636 times 10 to the negative 30 times 3 times 10 to the 8 squared. So this is equal to 6.8724 times 10 to the negative 13 joules. And then all this energy is provided to the alpha particle. So 1/2 the mass of the alpha times V squared is equal to delta E. So V is the square root of 2 times delta E over the mass of the alpha particle. So we get the square root of 2 times 6.8724 times 10 to the negative 13 over 4.0015 which is the atomic mass units, times the atomic mass unit, which is 1.66 times 10 to the negative 27. And this yields 1.44 times 10 to the 7 meters per second for the speed of the alpha particle. This was question 20 of paper 2, Advanced Physics 2 from 2021 in June. I hope this video is useful. Thank you guys for the really nice words I received recently. Many people request papers from the international GCSEs. At some point, I am thinking about uploading videos for UK GCSEs and other material. But again, guys, I mean, I'm not doing this full time yet. I wish I did. It would be really helpful for uploading more videos. But anyway, thank you for those who are providing nice comments. 90% of the people who watch these videos are not subscribed, so it would be really nice if people subscribe. Let me know what you think about the papers in the comments. If you have questions, let me know in the comments and I will reply. And yeah, see you in the next one. Good luck for those of you who are taking this paper on Monday. Bye, guys.